We're Team IPA and we're developing instrumented obstacles for a mobile robot. I'm Melanie Inoy.
I'm Josriel Pasikatan.
And I'm Kellen Adachi.
In a nutshell, the goal of our project was to create an accurate, robust, and versatile tool for developers of robotics platforms. The main focus of the project was development of what we called the obstacle. Essentially, a force sensor equipped wall that would provide a developer with a detailed, real-time feedback on how their platform is interacting with an object in its environment. We were also tasked with figuring out how to deliver data obtained from both the obstacle and a motion tracking system to the robot under test in real time. This would allow developers to reduce the amount of sensors on their platform and instead rely on external sources of data for things like navigation.
What follows are the 10 engineering requirements that the project needed to meet in order to be considered a success. We classified them based on what major part of the project they related to. These major components are the obstacle itself, the wireless communication system, and the Vicon motion tracking system. All of our engineering requirements were ultimately met.
The first group of engineering requirements are related to the obstacle and are as follows. First, the bumper system and the frame should be able to handle up to 100 newtons of force without breakage, warping, or parts coming loose. Second, the obstacle will weigh less than 50 pounds. Third, the force sensor measurements must be reported in 2 dimensions. The fourth requirement is that force sensors must be able to handle up to 50 newtons of force. And the fifth requirement is that force sensors will measure within 10% accuracy.
The next group of engineering requirements are related to the wireless communications and deal with the transmission distance and signal fidelity. Number 6. Information must be transmitted wirelessly from the obstacles to a robot up to a distance of 50 feet. Number 7. Up to 3 obstacles can be added to the system without causing problems with the wireless transmission.
The final set of requirements are related to the Vicon motion tracking system. Number 8, 2D robot location is tracked continuously with an update rate of at least 30 Hz. Number 9, 2D movement tracking is reliable of at least 1 meter per second. Number 10, cameras will track the 2D movements of the robot up to an accuracy of 1 centimeter.
Here is a top-level block diagram of our system. There are 3 major parts of the system, which we will give a detailed overview of later. First is the instrumented obstacle, next is the robot wireless receiver, and last is the server computer, which is connected to the Vicon motion tracking system. We will discuss the wireless modules as a group because of the similarities of the modules and because they work together as a system. The purpose of the physical obstacle is to measure the force applied by a robot when the robot collides with the obstacle's bumper. The bumper, which is part of the bumper module, is attached to a set of drawer slides, which in turn is mounted perpendicularly to another set of drawer slides. This design allows the bumper to move in 2 dimensions. Force is transferred along each axis to force sensors by springs. Using springs allows the transfer of force along the entire length of the slide instead of only at the ends of the slide. It also dampens the collision force to prevent damage to the force sensors even when up to 100 newtons of force is applied, which is one of our requirements. The force sensors output voltages which are read by the Atmega 128 microcontroller's analog to digital converters. The microcontroller serializes the data and sends it to the XP wireless module using UART. The frame consists of the board that the bumper module is mounted to, as well as the enclosure for the electronic components for the obstacle.
Since the system involves a constantly moving, semi-autonomous robot that needs to receive data, a wired data connection is obviously inadequate for this project. Obstacles may need rearranging, and dealing with cables, besides those for power, would be a hassle. XP wireless RF modules are used to handle all of the wireless communications with our system. The role of the wireless system is to transmit force data from the obstacle to the robot and to the server computer. The robot will have its own motion algorithm, but our obstacle's job is just to get the data to it. Data is also sent to the server computer so that it can be logged. While we were able to pass all of our engineering requirements regarding the wireless transmission, we did have a few issues when we added extra wireless modules to represent obstacles. These wireless obstacles were dummy obstacles that were not full-fledged physical obstacles and only included a microcontroller and a wireless module to broadcast pseudo data to simulate the appearance of other obstacles. Our implementation did not contain congestion or collision control, so the transmission delay factored into how much data each obstacle sent over a short period of time. Therefore, some obstacles would sometimes send more data more often than others. What we should have done was use a token-based system like TCP so that the data stream would be more balanced between the obstacles, and some measure of fairness could be implemented. Our system uses the Vicon motion tracking cameras for tracking and recording the robot and obstacle bumpers movement. The tracking system outputs the 3D location of the obstacles and the robot to the server computer, which stores the data. Pictured here is the array of 9 Vicon cameras. They are set up in a circle around the obstacles and the robot. Tracking dots are placed on the obstacle and robot, and when the cameras are set up and calibrated so that the cameras track the objects, they will track them with an accuracy of up to 1 centimeter, while an object is moving at up to 1 meter per second. While the Vicon motion tracking system is sufficient for application, we have also been working with the much newer Natural Point motion tracking system. The Natural Point motion tracking system is designed for smaller scale applications and features a modern usable SDK, which is more suitable for our application. We are currently developing an extension for the system to allow for visualization of the object's movement post-recording.
Hi, so today I'm having a short demonstration on our obstacle for robotics development, instrumented obstacle for robotics development. This is the obstacle itself. As you can see, the main feature of this obstacle is this rather large bumper plane here. This is the primary point of interaction between the robot and the obstacle itself. So what happens, the robot will come and hit the obstacle, and it'll register a force on these force sensors here. And basically, so you have one direction, boom, and you have another axis of motion here. So 2 axes force detection. Yeah, that's that. So next we have the electrical component of the project. So here is our microcontroller. It's an Atmega 128. And basically what it does, it coordinates the readings from the 3 force sensors and voltage, and converts it to newtons and sends them out through the XB wireless module here. And that's just a real simple XB wireless module and some circuitry to make that work. A level shifter, voltage regulators. It's very simple. And all that fits in this nice enclosure as such. And then finally, last feature of this thing is the wall wart. So it plugs right into the wall, provides 9 volts DC power for the whole obstacle. And yeah, very simple, very cheap, very effective. That's the quick overview of the parts and components of our obstacle itself. Hi, so today we're going to show you a quick demonstration of an actual data log and capture using our instrumented obstacle. So right here you can see I have my laptop, terminal window open, and again you're going to see this on the left side of your screen, the output of my terminal, so you don't need to really focus on that. But all I have plugged in here is the XB wireless server module. It's in this nice little enclosure and it plugs in by USB. Very simple. We have our obstacle here, and it's set up where we have a string attached to a pulley system to some weights, and it's pretty much ready to go. Everything's turned on. Let me just start my serial monitoring program. It's called Minicom. Okay, now it's running, ready to collect some data. Now I'm going to go ahead and plug in the module to turn it on. And already you can see that it's receiving data. Okay, so S0 is the force sensor in the center. Right, it registers what I'll refer to as our y-axis of data for now, and S2 is the left y-axis, so the negative x-axis. Sorry, force sensor, and S1 is the positive x-axis force sensor. So again, you see two directional, two axes force detection. All right. So what we're going to do now is we're going to drop this weight very slowly just to show you that the force sensors are accurate. So this is 25 pounds, and roughly at Earth's gravity, 9.8 meters per second squared, it should equate to about 110 newtons of force registered on our force plate. So my assistant Joss is going to drop the weights. And if you watch the S0 number, you're going to see that it starts climbing, climbing, climbing. It should settle at around 110 newtons, plus or minus 10% is our margin of error. And right there, right on the money, 111.6, 112.6 newtons. And that's reasonably accurate. So yeah, that's that. Again, the numbers will vary and fluctuate slightly. The sensors zero out at a different value every time we turn this thing on, so it takes a little amount of calibration to get them zeroed out and working right, but it's not too bad. The accuracy is pretty good. This is actually right on the money. So go ahead and pick the weight back up, and you're going to see that number drop back down to zero, or near zero, as that comes up. And it's still resting against the force plate, so it's going to register a small amount. And there we go. So yeah, I'm just going to go ahead and play with this thing a little bit, and you're going to see that as I push it harder, and the force will begin to increase and vary, and it'll depend on the direction that I push it in. So that in a nutshell is our instrumented obstacle, how it works and detects force.
From working on our senior design project for the past year, there are a few things that we have learned. Here are a few recommendations for future senior design students.
So number one, you definitely want to get late night access to Dearborn and the Senior Design Lab. If you guys aren't in there working 1 or 2 nights a week, very late, past 12, you're definitely doing something wrong. You'll definitely spend a few very late nights there. So you want to get late night access to both the building and the access pass to the room.
Also, be wary about working for customers outside of your major. Oftentimes they have expectations that are outside of the scope of the field. While it is good to explore something outside of your field, it may be hard to accomplish some of the tasks that they provide in a timely manner.
Number 3, make sure that your system requirements are well defined at the very beginning of your project to avoid scope creep.
And finally, like I said, you'll definitely be spending a whole lot of time in Senior Design Lab. Take some of this time to go and talk to the other groups about their projects, find out what they're doing. A lot of times you can find a lot of inspiration and solutions in the most unexpected places. Also, it helps keep you sane. You don't want to keep working on your project the whole time. Finding out about other projects is very interesting, and it's a learning experience. And as an added benefit, a lot of times some groups are doing worse than you are, and this makes you feel a little bit better about your own progress. Yeah. Alright, so we'd like to thank you for watching. This has been Team IPA with developing instrumented obstacles for robotics development. This has been
Melanie Noy.
Josriel Pasikatan.
and Kellen Adachi. Thank you for taking your time to watch this presentation, and have a nice day.